Okay, let's quickly review what we did yesterday. So we modeled the receiver system as a weakly nonlinear system, and we said we will model it up to the third order nonlinearity. Okay, and we put in a single tone and found out what happened to the at the output. And we found that if you put in a sinusoid, you will get components not only at the sinusoidal frequency but at harmonics of that also. Okay, so if the system was nonlinear, if the system were nonlinear, you will get if you put in omega, you'll get omega 2, omega 3, omega, etc. Okay. Apart from this, we found out that the terms DC, fundamental, etc. were changed by the higher order nonlinearities, right? Okay. So in today's class, we will figure out what happens when you put in two tones. So we take the same weakly nonlinear amplifier, let us say, and I'm going to put in two tones at omega 1 and omega 2, both of equal amplitudes A. Okay. So x of t is a cos omega 1t plus a cos omega 2t. Okay. So y of t will be alpha naught plus alpha 1 x of t plus alpha 2 x square of t plus alpha 3 x cube of t. Okay, so far so good. So alpha 1 x of t is pretty straightforward. At the output you will get alpha 1 a plus alpha 2 a. So alpha 1 a cos omega t. So I'll call that DC fundamental 1. So the DC term is alpha naught plus some portion from the second order terms. Okay, plus something. But now I'm going to assume that the input power that I give A, the input amplitude, is not very high. Okay, it's going to be so low I can neglect this guy. Okay, so I'm still looking at small signal behavior so far. Okay. What is the fundamental? Alpha 1 a cos omega t plus alpha 1 a cos omega 2t. Agreed? So if I were to look at the output, I definitely have omega 1 and omega 2, and I'll basically get amplified versions of the same. Okay. Now let us look at alpha 2 x square of t. 2 into, well, a squared into cos squared omega 1t plus cos squared omega 2t. Sorry, cos omega 1t plus cos omega 2t the whole square. Okay, so this would give me alpha 2 a squared cos squared omega 1t cos squared omega 2t plus okay. What do we know about these terms? So to keep the discussion relatively simple, I hope I don't need to expand out each one of these terms, but I just point out that omega 1t, if you remember, it is nothing but 1 plus cos 2 omega 1t by 2. Remember what we did in the previous class? So this will give me 1 plus by 2. This will give me 1 plus cos 2 omega 2t by 2. What does this give me? What is 2 cos omega 1t cos omega 2t? Cos of 2 by t. Okay, so this will give me, okay, so let me do one thing. Give myself some space. Okay. Now, we know what these terms are. This half term r squared by 2 from each one of these terms. We'll go back and fold down to change the DC value. That's pretty straightforward. This term here gives me a second harmonic of omega 1. Okay. This gives me second harmonic of omega 2. Okay. Now, these two terms, cos of omega 1 plus omega 2t and cos of omega 1 minus omega 2t, are called intermodulation terms. Okay. These are called intermodulation terms. Okay, so these are called second order intermodulation terms. Okay. Or IM2. IM2 terms. Okay. What do I mean by that? So in general, now you can extend out because we are going to start looking at it. If you get P omega 1 plus or minus Q omega 2 terms, right? You will in general get it for a higher order nonlinearity, where P can range from 1, 2, 3, 4. Q can also range from 1, 2, 3, 4. Right? So this can give you IM2, IM3, IM4, etc. depending on the value of P and Q. Okay, so they are also intermodulation terms. So any component that falls at a linear combination of omega 1 and omega 2 are called intermodulation terms. Okay, the order of the intermodulation depends on P and Q. It is basically P plus Q. Make sense? Okay, so that is a specific term which you will see being used again and again in RF systems. Now, what about cos cube omega t? Let us go to the last term, alpha 3 x cube t. Okay, is nothing but alpha 3 into cos omega 1t plus cos omega 2t the whole cube. Okay, so it is alpha 3a cubed into cos cube omega 1t cos cube omega 2t plus what? 3 cos squared omega 1t cos omega 2t plus 3 cos omega 1t cos squared omega. Okay. Okay. So let us again start listing these one by one. What is this? So go back to yesterday's class. We expression 3 cos omega t plus cos 3 omega t by 4. Okay. Okay. That's great. Okay. Third term. So 3. So you get cos omega 2t into what is cos square omega 1t? 1 plus right 2 plus. I'll just make a note that these are the other terms. 3 Is that okay? So far so good. What are these terms? Again, this changes the fundamental gain. This gives you a third harmonic component for omega 2. For omega 1. This changes the fundamental gain for omega 2. This gives you a third harmonic term for omega 2. So far so good. What are these guys? Now you can see this term here also changes the fundamental gain, and so does this for the individual component. Okay, that's also okay, but we are specifically interested in these terms. Okay, I am interested in these terms. Okay, what does this give me? 3 by 2 cos omega 2t cos 2 omega 1t. Correct? What is that? What is this? 3 by 4 cos of 2 omega 1 plus or minus omega 2. Okay. What does this give me? 3 by 4 Make sense? What are these guys here? These are IM3 components. Okay. So now we have identified for this weakly nonlinear system, we have identified all components of the output. If I were to, in fact, omega, look at the output y of t, right? So I think let's start from one by one. You'll get a DC component. Let's ignore that for now. Okay. You will basically get omega 1, omega 2. Okay. What else do you get? You get from the fundamental terms alpha 1, you get omega 1, omega 2. Term, what you get? Let's go back and quickly check this. You got 2 omega 1, 2 omega 2 and omega 1 plus or minus omega 2. Agreed? Right? So 2 omega 1 would lie somewhere here. 2 omega 2. Okay. Omega 1 plus or minus omega 2. Where will they lie? Where will omega 1 plus omega 2 lie? In between. Okay, you will get some component. Where does omega 1 minus omega 2 lie? Very close to DC. At delta omega actually. If this was at delta omega, you will get okay. So remember that this is delta omega. Okay. What next? The third order components. This, of course, we already shown the fundamental omega 1, omega 2. You get 3 omega 1, 3 omega 2. Okay. Three omega 1, yes. Yeah, we are going to do. We have not come to that yet. Huh? No, I'm just going based on the expansion that we did from the DC alpha 1 term, alpha 2 term, alpha 3 term. That's the way I'm going. But okay, so the alpha 3 x cube of t term will give you 3 omega 1, 3 omega 2. It modifies omega 1 and omega 2 terms. We can't. That basically changes the amplitude. But apart from this, we saw that it gives you 2 omega 1 plus or minus omega 2 and 2 omega 2 plus or minus omega 1. Okay, so what are these terms? This is equal to 3 omega 1 plus delta omega. Okay, and what is this equal to? 3 omega, right? So clearly they will lie somewhere here. Okay. Agreed? So you have 3 omega 1 plus delta omega and 3 omega 2 minus delta omega. And finally, you have 2 omega 1 minus omega 2 and 2 omega 2 minus omega 1. So 2 omega 2 minus omega 1 is nothing but omega 1. Huh? No, you can say what is it? 2 omega 2 minus omega 1 will be omega 1 plus 2 delta omega. Okay? 2 omega 1 minus omega 2 will be omega 1 minus delta omega. Yes, that's the same thing. It's the same, right? Because he expressed it in terms of omega 1, I express it in terms of omega 1, right? So as you can see, your components lie at exactly delta omega from this. So these are your IM3 components. Now, it turns out, for the purposes of our analysis, in the present context, these two terms shown in blue are of paramount importance. Why is that? Huh? Yes, so now you can see that if you choose delta omega to be very small, okay, these two terms, 2 omega 1 minus omega 2 and 2 omega 2 minus omega 1, these two intermodulation terms actually fall very close to the original signals in band, effectively, inside the bandwidth of operation of the amplifier or filter or whatever circuit it is. Okay, so the IM3 components fall in band if your delta omega is small. Make sense? So now you don't have to worry about the frequency response of your system, okay? Because these components, these two components, will be functions of the nonlinearity of the system. Their amplitudes, if you did not have a third order nonlinearity, you will not get this component at all, because it depends on alpha 3. Make sense? Now, so now this is a standard way of characterizing the nonlinearity of narrowband RF systems. Okay, whether it's the overall system or just components of the system. If you have an amplifier and a narrowband amplifier normally, you want to characterize this nonlinearity. It is going to be used as a low noise amplifier. You would characterize using this by applying these two tones, okay, in a very specific way. Okay, now what I'm going to do, I'm going to plot. You remember we plotted output power versus input power. I'm going to plot that again. Okay. In dB. Okay. Remember the curve that I got. I got something like this, where the y-intercept was the gain of the amplifier. That's all great. Okay. Let me redraw it slightly better. I'll redraw it like this. What is the slope here in dB terms? 1 dB per dB. What is the y-intercept? G. So G for our amplifier, it is somehow related to 20 log alpha 1. Okay, alpha 1 is the small signal voltage gain. Okay, so it is somehow related to 20 log alpha 1. That's all we know. Okay. Now, on this same plot, I am going to plot the amplitude of the third order intermodulation components. Okay. I'm going to show that in blue. First question. So what is the amplitude of the third order intermodulation component? 2 omega 2 minus omega 1 and 2 omega 1 minus omega 2. 3 by 4 times alpha 3 a cubed. Okay. So the amplitude of these guys. So now I'll go back and mark it here. Both of them are equal. Okay. What is the value of this guy? Alpha 1a. The fundamental I'm interested in omega 1, omega 2 are both at alpha 1a. The third order intermodulation are at 3 by 4 alpha 3 a cube. So, if I were to, on this plot, I'm going to plot the amplitude. Now, this is basically changing A, the input power. A stands for the input power. What will this curve look like? Huh? Okay. We have drawn this curve already before, couple of classes before. What I did was, I plotted P out versus P in. The slope of that was 1 dB for BB, because the output voltage was the voltage gain A times the input voltage. Correct? The output power was related to A squared times the input power. I took 10 log of this. The intercept was somehow the gain, power gain of the amplifier. I get a straight line for small signals. Afterwards it compresses. Because I am plotting output power of the, even though the amplifier could have been nonlinear, I was putting in omega. I was monitoring only omega at the output. I hope you understand. Okay. So I got this term. Now on the same plot, I want to also plot the amplitude or the power of the third order intermodulation term. You understand? It will be shifted down. Will it be a first? So now let's start from there. Is it a straight line or is it something else? Assume, so now apply small signal approximations. Assume I am putting in very, very small amplitudes at the input. A is extremely small. Let us do that first. I know that at very high amplitudes, the third order term itself will compress for sure, because I'll get components from the fifth order term, seventh order term, etc. Right? I don't want to look at that. Okay. In fact, in a couple of minutes, you will see that the definition of this type of nonlinearity does not care what those terms are. Okay. Now, I make A extremely small. So, I am now operating somewhere here. Okay. A is very small in this region, let us say. First question, what is the amplitude of the IM3 component? Alpha 3, 8. Okay. If A was very small, and we saw that if your amplifier is weakly nonlinear, we saw that alpha 3 should be much smaller than alpha 1. And if A is very small also, first of all, the magnitude of the third order intermodulation component should be extremely small. Hopefully, if you choose A properly, it will be much lower than fundamental. I hope all of you agree. Right? If it's a weakly nonlinear, if it's a strongly nonlinear amplifier, you're already done for. Right? So, you may start somewhere much lower. Okay. Next question. I am plotting on an axis which is dB for dB. Okay. So, now, what will be the now, if I increase A, let's say I make A 10 times what it was before. Okay. So, in other words, I am increasing the input power by 20 dB. Okay. How much will the output IM3 power increase by? By 60 dB, because it is A cubed, related to A cubed. Okay. So, you will, but it will follow linearly. You will basically get something that will give you a sign for this IM3 amplitude. Every time I make A 10 times, okay, A cubed term will go by 10 cubed, right? So now I will get a straight line which will have a slope of 3 dB per dB. Does that make sense? Yes. Power is amplitude squared and then you take 10 log. That's why I said you increase it by 10 dB, you will get 60 dB. Power goes, if you make amplitude 10 times larger, power will become 20 dB higher, A squared, 10 log of A squared, and then the other one will go by 60 dB. So you will get 3 dB per dB increase. So the slope of this will be 3 dB. This will increase much faster than the fundamental, because one is increasing as A, the other is increasing as A cubed. Okay, number one. Number two, of course I know at very high powers this will also compress. Okay, so eventually I might even show that. I'll show this compressing in some form. But in the small signal region, it is going to be a straight line. Okay. Second thing, if I compare two systems where one had a lower alpha 3 than the other, what will happen to the IM3 curve? This is the IM3 curve, okay. If I take two amplifiers, one is more linear compared to the other. Yes, so the whole blue curve will shift downwards. You understand? The blue curve will shift downwards so that since the amplifier is more linear, the magnitude of the third order intermodulation components will be lower, because alpha 3 is lower for the same amplitude. So this curve will shift downwards with decreasing alpha 3. Okay, that is the other thing I know. Now, the way we are going to define the nonlinearity is to now take the small signal regions. I'm not going to worry about the compression at all. I'm going to take the two small signal regions. I'm going to extrapolate the fundamental as a 1 dB per dB line. I'm going to extrapolate the third order IM3 curve as a 3 dB per dB line. I'm going to find out the point where they intersect. You understand? So, in my ideal 1 dB per dB line and the 3 dB per dB line, in the region where they are not compressed, where neither of them is compressed. Okay, I'm going to extend it to the point where they meet. This is a fictitious point, obviously, right? Because you can never ever operate the amplifier at that point. The fundamental would have long since compressed, would have long since compressed. Okay, so it is a fictitious point. However, if I were to take a more linear amplifier, it would have a curve like this, maybe something like this. If I were to extrapolate the curves, you can see that they would meet at a higher point. Okay, so now you can see that the point where they meet tells you something about the linearity of the component of the system. Does that make sense to everybody? Okay, the lower the nonlinearity, the larger the power at which they will meet, whether it's input power or output power. Okay, so this I'll go with the original curve. These two terms now. So this point is called the IIP3 or input referred third order intercept. Okay. Yes. If you compare them with the same fundamental gain, you are comparing them only for gain, not for nonlinearity. I take two amplifiers which have the same alpha 1 but different alpha 3s. If the alpha 1 is different, then you will find that this input referred intercept also tells you about whether it's more linear or not. The reason is you are now extrapolating the two and finding out where they meet. So you will find that the actual value of IIP3 is a ratio of and alpha 1. Okay. This is called the OIP3 or the output referred third order intercept. Is this okay? Any questions so far? Okay. So the definition itself is simple. Okay. Now you can see, if you had any circuit, you want to describe its any narrowband circuit, an RF circuit, you want to describe its nonlinearity, you will very specifically use this because the third order intermodulation component falls in band. Okay, you can choose of the two amplitudes. Now when you design a real amplifier, you may find some small asymmetry between the two halves because the amplifier itself may not have a narrow band response. Amplifier itself may not have a flat response. So you may see slight power differences between the two. That will give you some small slight differences in IIP3 depending on whether you take the 2 omega 1 minus omega 2 component or the 2 omega 2 minus omega 1 component. Okay, it should be very slight. If you see a difference of 5-6 dB, then there's a problem. If you have a difference of half a dB, 1 dB, etc., that's all within the margin of error that you expect anyways. Okay. Yes. Because, good question. So she is asking, how do you have control over alpha 3? Of course, if you were to build an amplifier, the nonlinearity of the amplifier is a function of the bias current and voltage of the transistors. Okay. Now, and of course the power supply. Okay. For example, you remember that, if you take the Taylor series expansion of the, go back to beginning of analog circuits 3002 course, we took the transistor, or in fact any two port, it doesn't matter for the transistor. You take any two port, take the second order term. That tells you the error in your linear. Okay. Now that term should ideally be small, and you will find that that is related to the bias of the device itself for a MOSFET. Okay. Typically for a MOSFET, it will be related to the VGS minus VT of the device. Okay. Please go verify that for yourselves. With the second order, calculate the nonlinear term. Now that term, that nonlinearity can be modeled as a polynomial nonlinearity for any amplifier. If you have done a good job, it will be weakly nonlinear. So that alpha 3 will be very small. If you change the bias currents, voltages and power supply, you will change alpha 3 for sure. Okay. Any other questions? Okay. Now, the test for IIP3 is now clear. I now put in two equal tones into my amplifier, two equal in-band tones. So let me write down the procedure. This is often called the two-tone test. As I mentioned last class, a tone is basically a frequency component. Okay, I put in cos omega t into any component. It is called a single tone being applied to the input. A tone is a frequency. Even from normal parlance, you know that, I think, right? Okay, but the important thing, wait, I'll write it, reword it slightly differently. Apply two tones, omega 1 and omega 2 of equal amplitudes. Choose delta omega to be small. Why is this important? Because the smaller you choose delta omega, the closer will be the IM3 components to your fundamentals, so that bandwidth effects of your amplifier, filter, whatever component it is, will not affect your measurement. Make sense? So it is important to choose A also to be small, so that you get the appropriate linear curves when you versus P in. You had a question? Okay. plot P out versus P in. Okay. And here in dB, and this will give you of course the fundamental will be linear with, and that is where choose A to be small, the previous point comes in. Okay, I'm just putting down and writing what I mentioned earlier. What do you mean? What do you mean by that? No. In fact, these curves, P out is the P out of the fundamental or the third order now. Now you are plotting on the same curve, the third order, right? So we are basically not plotting out total P in at all, total P in out at all. In the case of P in, you are applying it, you are only applying two tones. So P in total is the same. P out, you are plotting only the fundamental. Okay. So if you were really measuring in the lab, what you would do, you would have an estimate of how linear your amplifier is already a priori. You would probably follow this up with a highly linear filter and then pass it into a spectrum analyzer to figure out. Otherwise, your spectrum analyzer may also be linear enough to show it properly, in which case you take the output and monitor only the in-band components. Any other questions? I'm just writing down what we discussed earlier. Okay. Extrapolate. The two curves to meet at this point. You don't need to do two separate tests. One to find out the fundamental, one to find out the IM3. Because if you monitor the amplitude of this guy, that already gives you the fundamental. So what you are plotting on those two axes is alpha 1 A 3 by 4 alpha 3 A cubed. Make sense? Okay. Now, before we disperse for the day, I want to calculate the value of IIP3. How do I calculate it? For this system. Fundamental? Equal. So by definition, the IIP3 point is the value of the input for which the fundamental is equal to the third order value, third order intermod product. So what is the fundamental value? So let us say I apply in A cos omega 1t plus A cos omega 2t. Okay. So what is this? This is alpha 1a. This is just a small signal value. Okay. So what I could say, now I'm going to call this amplitude as the AIP3. Okay. This is the value of the amplitude corresponding to the input referred intercept point. The IIP3 is actually a power value. It is not an amplitude value. Okay. We have now taken, because we are working with circuits, we have now taken it referred to some amplitude. we are taking it to refer to some amplitude. If you are designing a 50 ohm system, you can refer it back to 50 ohm system to get the power value. Okay. Okay. What is IIP3? Make sense? Now you see that if alpha 1 were different, it doesn't matter. You can still directly compare alpha 3 because it tells you for a given gain how much the third order, how much lower the third order nonlinearity. Okay. And of course, what is the value of the power? IIP3. If you referred it to some resistance RS, let us say. What is the IIP3 in power? This is the peak voltage, right? Peak amplitude. So A IIP3 by root 2 the whole squared by RS will give you the power. So what will it give you? Okay. With reference to some RS, will give you this. So specifically, I will also write this as I'll write it in this form because you are always plotting the magnitude, remember. Any questions? Okay, we'll stop here because I'm late for the next class. So we'll stop here and continue. Tomorrow we have a class, right? Do we have a class tomorrow? Okay, we'll continue tomorrow's class. Class is still up in the air. We'll decide tomorrow.